pleasure to have Dave speaking again. I think some of you were here when Dave sort of came and gave a talk at camp for the first time. For those of you who haven't been around or who weren't around for that time, so Dave Goldberg was at Georgia Tech for many years, and for a long time, many other places, including Cornell, were trying to figure out ways of getting him to come here, there, and then finally we figured out the secret, and so he's here. To give you a sense of how much difference that makes in our daily life, so we have this big conference in OR called Infimum, and usually Cornell sort of throws a gathering at Infimum, and it used to be this very staid affair in a ballroom with everyone standing around, and then Dave comes, and then the first year he's here, he decides to do the same party in a bar, and like it just completely changed the atmosphere of the place. But the other thing that, I mean, of course he does great research, all that, you'll see all of that stuff, but the other thing which has notably changed in the department since Dave has come is earlier when we used to have seminars, they used to be fairly staid affairs. People would come and talk and nobody would say anything. And now once Dave arrived on the scene, it has become much more like a competition. Quite often people don't get too far into their talk because Dave will interject. And one of the reasons we are having him speak right now is so that we can... You have been warned. If he gets past page 5, we will consider this a failure. So please be on your worst behavior.
Yes. Very good. Thanks, Sid. And I have very much enjoyed my time here so far. And I'll dig right in. But yeah, I do like to keep it really informal. So any questions, thoughts, comments, either raise your hand or just yell at me. It's okay. So today I'm going to be presenting on a piece of work that I call Beating the Curse of Dimensionality in Options Pricing and Optimal Stopping. This is joint work with an excellent Ph.D. student, Yilun Chen, who's an ORI student here. And so I'm going to try to express the high level to you at the very beginning, and let's do that. And I just preface this by saying this is what we're really excited about. We think it connects to many other kind of control problems and problems in finance and just operations generally that people might be looking at. And if after the talk people have any thoughts or follow-up, feel free to send me an email. I'm here and I'm happy to talk about it. So there's also a very interesting connection to network flows that I'll talk about at the end for anyone who works in that kind of space. So what's the punchline? So options pricing and optimal stopping is a central problem to financial math, operations research, applied probability, etc. Now, I assume at least some percent of the people in the room have seen this so-called optimal stopping problem, which roughly says you see some things over time and need to decide when to say stop and pick the one you're looking at in an online way. Now,
why do you take a vote and see?
How many people have...
That's a knowable thing, how many people?
Okay, I like it. Look, we're getting off to a good start, right? Can you raise your hand if you've never heard of optimal stopping at all?
Never heard of or never seen it?
Well, seen it in what? In action?
Seen it in equations, know anything about the calculations. I've heard the words, but I've never seen it. What do you mean?
I mean, have some vague familiarity. I'll take most people seem to have some vague familiarity.
No, I have to find out.
Never experienced it.
Okay, can you raise your hand if you've never seen any equation associated with optimal stopping? Okay, fair enough.
Now what are you going to do?
Fair enough, all right. Well, then you're really going to learn a lot. So it's a huge opportunity for me and the people that just raised their hand. Very good. But I did get all but one had heard of it at least vaguely. Right? So for those who raised your hand, you've never seen an equation. Most of you, can I get kind of a nodding of heads, have heard of it vaguely? Okay, good enough. We can work from there. Very good. So for those of you who have heard of it vaguely, and even for those of you who may have seen an equation or two, I think there's generally, when people are exposed to this, especially, for example, in maybe an advanced undergraduate class, a first-year PhD class, or kind of certain lines of literature, you'll see it explained as kind of a very stylized toy problem, where they say, okay, you're seeing uniform random variables over time, and based on their values, their IID, you need to decide when do you say, I take this one.
What's IID?
Oh, you got me again? Okay. IID would be independent. Oh, we've really taken the mantle up here. All right. IID means independent and identically distributed, which would just mean you see kind of uniform 0, 1s over and over, and they're unrelated, let's say. Very good. And so, yeah, many people have probably seen that. It sometimes goes by the heading of the quote-unquote secretary problem. It's been in popular media, etc. And some of you may even know, I'll do a little poll. Can you raise your hand if you are in some way vaguely aware that there's some way to look at the secretary problem so you get something called like the 1/E rule or something like this vaguely? Okay, maybe over half of people. Okay, very good. So, okay, that's fine and that's nice, and that is a nice little stylized model that is insightful in its own way. However, it turns out that for many settings in the real world, especially as it intersects with mathematical finance, but also certain kind of high stakes, high dimensional control problems arising in medical applications and elsewhere, it turns out that the kinds of decision-making, so-called optimal stopping problems you get are not so simple. Namely, instead of just seeing these kind of independent things over time and based on those one-dimensional values having to decide when do you stop and take the one you're looking at, instead, in a typical, for example, a mathematical finance application, you might be looking at a high-dimensional vector of complicated economic information, including stock values, economic indicators, other things evolving in a complicated way over time, and then somehow based on that high-dimensional information set, which is evolving stochastically over time, you need to decide, do I stop and execute some kind of financial option now, or do I continue and gamble, I'll be able to do better in the future. And furthermore, a lot of times those problems, in particular, this high-dimensional information set, is not even Markovian. You can imagine, of course, in general, the value of stocks tomorrow is not totally independent from the value of stocks today. And in particular, you have essentially a certain kind of history dependence or path dependence, so it's very far from just some kind of Markovian setup, etc., and it's high dimensional. We'll make this more precise later, but again, the thing I want to convey is in many of the stylized models you may have seen, you just see these kind of independent random variables, and based on these one-dimensional things, you have some threshold that says stop or not. In the real-world applications where this is very much of interest, instead you have a complicated, high-dimensional, kind of random vector-type process evolving over time, and based on observing that, you need to decide, do I stop now or not, and execute something. And so, in other words, the real-world problems are actually computationally intractable because of that high dimensionality. And in particular, for those of you who have worked in control or certain kinds of optimization, you'll know this is generally called the so-called curse of dimensionality, because if you wanted to do kind of naive dynamic programming, you would have to look at every possible kind of complicated history you might have seen, and you can't do that even on kind of the fastest computers out there. So you can't solve the dynamic program. Now, one might think, okay, maybe this is some kind of obscure math problem. It turned out, especially after the kind of 80s and the 90s, when certain kinds of things related to options pricing really took off in math finance, that exact kind of simple, I'm looking at this high-dimensional kind of process evolving, do I stop now or do I continue, became like an extremely popular fundamental building block of high-dimensional control. And so there's like thousands, maybe tens of thousands of papers across multiple academic communities, again, because this core problem of how do I look at a complex kind of high-dimensional information process and based on that decide when to execute a kind of decision which has meaningful implications. Again, because that arises in so many applications, including math finance, there's actually many academic communities that have looked at how would we actually go about solving this because we actually want to for actually real-world kind of applications. And so many academic communities have looked at this. It's kind of maybe generally been perceived as of all the kind of genuine high-dimensional control problems, it's in some ways the simplest non-trivial one that it was generally assumed is intractable. Because, okay, in general, a high-dimensional control, you might be making many decisions in weird ways over time. Here, it's pretty much you're just going no, 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 and then you go yes at some time. So it's kind of this core building block of kind of more complicated high-dimensional control problems. Anyway, many communities have written many papers on this using techniques ranging from approximate dynamic programming, which says roughly instead of trying to solve that dynamic program, you try to massage it in some way to make it more tractable and do something there. There's simulation-based methods, there's duality-based methods, there's PDE-based methods, many methods out there. And each has something interesting to say, lots of interesting papers there. However, if what you want is computational tractability plus proofable error guarantees, so you want to have an algorithm that is provably efficient and provably has small error, it turns out to date, none of these approaches have been able to formally achieve that. And that's especially true for things that are high dimensional and also fully history dependent, like the things we're going to be talking about here. But that's even true when things are high dimensional and say it doesn't depend on the history necessarily, that's still true. Namely, it's still, even though there's all these papers looking at this, all these different approaches, pretty much the breakdown in the literature was, okay, this is a truly important problem, so we want to come up with maybe heuristic ways to approximate that dynamic program or use simulation, etc., to try to come up with numerical answers, numerical schemes, which maybe we can show give an upper bound or a lower bound, and maybe we can show our scheme is efficient, but we have no way to guarantee that it is actually close to the optimal value or optimal policy. Alternatively, especially in kind of more pure math, has anyone heard of something called, can you raise your hand if you've heard of the Snell envelope? So a few people, okay. So I'll simply say that even on kind of the more pure mathematical side, there's a whole literature about understanding certain theoretical aspects of these problems and kind of very well-developed theories and duality and these kinds of things, but they're really not computational. So they don't yield efficient algorithms. And if you want both of these things, efficient algorithm plus rigorous error bounds, there's really nothing to do. And I'll talk about why a little bit later. But the bottom line is, again, in some ways this is kind of the core problem for which people would say, well, it's a genuine high-dimensional control problem. Of course there's not an efficient algorithm. Thousands and thousands of papers coming up with kind of numerical methods for this are effectively premised on the understanding that it is theoretically intractable because it's a high-dimensional control. If you don't make kind of additional assumptions, it will be just fundamentally intractable. I mentioned already that there is kind of a fairly well-studied duality approach to this problem. I won't kind of go into the details of that. I'll simply say, and I'm happy to talk after the talk about more details with that. It turns out that in the classical literature, if you try to write down kind of a certain dual approach for this, instead of finding stopping times, it turns out you're searching for martingales with some properties. The bottom line is there is a large literature on that, but most of our understanding of these kind of dual approaches is very non-explicit. It's kind of, in many cases, abstract, maybe even non-constructive. There are a few counterexamples to that, but even those counterexamples are at least not computationally oriented. So there's that. And one thing I want to say about what is a major hurdle for most past approaches is that this actually relates to what some of you may have seen for the secretary problem. So how does one typically go about solving, I'll take a little digression now. The secretary problem, you roughly say, well, if I'm in the last period and I haven't stopped yet, please.
Sorry, could you define the secretary problem for those who have not heard about it?
Yeah, okay, so the secretary problem roughly says, imagine you have a fixed time horizon. In every period, you see a uniform, 0, 1, for example, and you're going along, and you need to decide in each period, if you haven't stopped yet, do I stop and settle for the one I'm looking at? Where if by the end you haven't stopped yet, you must settle for the one at the end. So, you know, at the very beginning, maybe you see one. Yes.
That's perfect. I mean, you in random order. If you are seeing one over E, that's random.
There's many variants of the secretary problem.
Yeah.
I'll simply explain the
The easiest.
easiest version of them. Yes, there's any number of, I suppose the 1 minus 1 over E, as it's kind of classically originally taught, would be looking at a random permutation, but it's philosophically the same, and so I won't dwell on precise differences, but thank you for pointing that out. And it's kind of, yeah, most easy, that's kind of the core understanding of the secretary problem.
So just to make sure I understand,
Yes.
I'm interviewing people one after the other.
Yes.
And for each one of them, I'm seeing some one-dimensional value which characterizes how good of a fit to the position that person is. And they're assumed to be IID, so they all follow some distribution about which I know in
Sure.
advance. And I'm deciding when to stop this process.
Yes, that's right. Let's say, yes.
And I cannot, if I skip this candidate and wait it until later, I cannot say, no, wait,
You can't
I
go back
wanted
in
the
time.
person. Okay, good.
Yes.
Thank you.
And again, as Sid pointed out, thank you. There are many variants of this, and some do have to do with these concepts called relative ranks and these kinds of things. These things tend to yield pretty similar results, and so I'll simply go with that level of understanding for here.
Okay.
Now. Good, thank you. But yeah, the point I wanted to get across was that when everything's one-dimensional like that, it's very natural to solve that problem by backwards induction, where you reason, well, if I'm standing at the end, I know I have to settle no matter what. Then you say, well, suppose I'm one period away from the end. Now you reason about, well, I know what I have to do if I pass this time. And so you can kind of get these equations going backwards and use induction to kind of solve the dynamic program recursively in a natural way. And I assume, can you raise your hand if you've ever seen some kind of backwards induction argument to solve something kind of like that? Okay, I'm almost there. The problem is that when you get to genuinely high-dimensional problems, the backwards induction methodology no longer works because there's too much to keep track of. And even if you try to be clever and solve it in some kind of, well, I'll use simulation and kind of go backwards so I don't need to keep track of everything somehow, the error blows up and it's still intractable. And that's a dimensionality issue that we call fully nested conditional expectations. Namely, when you try to do the backwards induction but you're high dimensional, by the time you get all the way to period 1, if you actually look at your solution, you will have conditional expectations that are nested in order of times equal to the length of the time horizon. And that leads to kind of an error propagation and various undesirable properties that make it effectively not usable in algorithms. Arthur, yes?
Can you maybe give an intuition for why this approach of using Monte Carlo to do rollouts fails? Because usually that's what fixes it.
Yeah, good. So it's because,
Can you repeat the question in your own language?
the question just asked.
Yes.
Yes, he was saying, can you give an intuition about why this nesting, this backwards induction doesn't work?
Specifically if I do Monte Carlo.
Yeah, so if you
about
try to do it
dimensions.
by Monte Carlo, roughly the problem is this. With every level of nesting, for every sample you want here, you need to do a bunch of branches of the next level in. And so then this level of branching is kind of growing exponentially with the depth that you want in some sense. Yeah, that's, maybe can explain more after the talk, but I think for now let's leave it at that. Great. Okay, so what do we prove? We prove, somewhat surprisingly, there's actually what I hope to convince you of is a quote-unquote simple and elegant formula for this intractable problem as an infinite sum. Which at first glance is a little weird because I just told you it is a hopeless computational problem, and now I'm telling you it effectively has a simple analytical formula. So that's a little weird. But maybe I'm cheating here. It's an infinite sum. Maybe it's just kind of a math thing, which maybe it's cool, but maybe it's not computationally useful. What I'm going to show you is that if you take this infinite sum and truncate it after k terms, we will be able to bound the error by 1 over k. And furthermore, each of these terms will be easy to simulate in a way that I will make precise. For this reason, what we come up with is a way to express the optimal value of a high-dimensional optimal stopping problem, and also we get good policies, and I'll make that precise in a bit, effectively by using this representation we come up with and truncating it, and then realizing that each term of that summation, each term of that series, can be simulated. This yields efficient randomized algorithms for this problem. Effectively, for those of you who are familiar with kind of algorithmic complexity theory, we effectively get polynomial time approximation schemes for this seemingly intractable high-dimensional optimal stopping control problem. And these are really the first results of their kind. And in particular, for any error parameter epsilon, so say you're willing to tolerate an epsilon loss of optimality, we come up with a time that's an algorithm whose runtime is effectively t to the 1 over epsilon, which will yield a value that is within epsilon of optimal. Equivalently, we come up with a stopping strategy that you can implement in time horizon to the 1 over epsilon, which also is within epsilon of optimal. I'll make precise the notion of epsilon of optimal a little bit later.
What is capital T?
Capital T is the length of the time horizon.
Okay.
Epsilon of optimal, you mean additive or
Yeah, I'll make that precisely. It depends on precisely what you want to say and exactly what you want to assume. The general methodology doesn't require any restrictions essentially, but depending on what kind of error you want, then you kind of, at least as our current results, you have to tweak things a little bit. So I'll make that precise a little bit later. The other thing I want to say is this method does not require knowledge of any joint distributions or densities or anything like that. All it requires is access to a certain kind of simulator which allows you to simulate that high-dimensional information process. Because again, as I said before, this infinite sum here, each term of it is a certain kind of expectation which can be computed by simulation, effectively only given access to a simulator that can simulate that high-dimensional underlying information process, and so that's another nice feature here. And I hope to convince you that if you put this all together, we truly, for the first time, and it's quite surprising because it was assumed that it could not be done, that truly here we beat the curse of dimensionality, and this is really a setting where it was not believed that this would be possible. We will also show that, interestingly, effectively, the entire very elegant theory of duality for optimal stopping, which I said certain mathematical communities have developed over the last 50 years or so, actually can be totally recovered by Max Floh-Min-Cut. And it turns out it's actually a fairly intuitive connection. I will explain a previously unknown connection between high-dimensional optimal stopping and min-cut. And again, it'll be very intuitive, and interestingly, it draws kind of a sweeping connection between two very well-developed duality theories, and I think there's a lot more going on there. I'll also say that, interestingly, this approach we take with infinite sum and truncating and all these things, it can be viewed as a very clever way of pushing flow through a very special network which arises in optimal stopping problems if you look at it the right way, and doing that. So in other words, our whole method can be interpreted as a very special kind of flow method in some sense. And again, we think this should be broadly applicable across many other high-dimensional control problems. We're thinking very hard about that. And if, again, anyone has thoughts, etc., please shoot me an email. So we're happy to take questions after the talk. So with that punchline, which as Sid had warned you could take almost the whole time, let me get into the model. Let me first double check that we have till 1/2 here roughly. Is that roughly, is Erica here?
We have until 5:20.
Okay.
Oh, sorry, 4:20.
4:20, so 25 minutes. Okay. So let me explain the model then. I won't, there's certain details I'll omit. So we're going to stick to a discrete time model where you know the time horizon. And again, in every period you're saying kind of, do I stop now if I haven't stopped yet? We're going to assume that you have this high-dimensional information process, y1, y2, y3, up to yt, where even though we don't require it to be kind of a capital D dimensional vector of real numbers, it'll just be easier to think about it. So suppose that this information process is this vector valued process, y1, y2, y3, y4, etc. We'll denote the dimension by capital D. That might be quite large. You should think about it as being roughly as bad as polynomial in the length of the time horizon. So we want to think about the setting where the time horizon is kind of large and the dimension may also be kind of large in that way. And again, we want to think about this information process as evolving in a possibly very complicated non-Markovian way, so it's a high-dimensional kind of a general stochastic process. Okay, and we let F be the filtration generated by this process. So for those of you who maybe aren't familiar with filtrations, you just say that's all the information contained in the first little t vectors is script f sub t. Okay? Good. We'll assume there are some known cost functions, g1 through gt. It turns out, for reasons related to that connection to max flow min cut, the minimization version of this is actually a little more intuitive to explain our framework in. So we'll stick to cost functions. And the general setup we have will be that if you stop at time t, the cost you incur is cost function g little t evaluated on the first little t high-dimensional vectors, where we use the notation y sub bracket t to denote y1, y2 up to yt. Okay? So GT is a mapping from kind of these submatrices.
For the secretary problem, that would be the current value.
For the secondary problem, that would be the current value. Yep. So there, capital D would be 1, and GT of YT would simply be the current value, yes, which would be that one-dimensional number. Very good. Great. And we call that capital ZT just as a notational thing. It is random because Y subscript bracket T is random. And just for simplicity, we'll make it non-negative and integrable, so we won't worry about technical things like that. Good. We will let script T be the set of what we'll call F-adapted stopping times belonging to the interval 1, t. What is an F-adapted stopping time? It simply means based only on the y's you've seen so far, you need to decide, do I stop now and accept cost, the current g evaluated on the y so far, or do I continue? Kind of a stopping time is a strategy to do that. Script T is the set of all such strategies. Okay? In which case the problem of interest is, over all such strategies, pick the one such that if you play that strategy and stop according to that strategy, you incur the smallest expected cost possible. Since we're talking costs, you want to have the least cost possible in expectation. And this is effectively the most general setup for kind of high-dimensional optimal stopping because we allow kind of a general information process. There's no assumptions about the cost or densities or decays or anything like that. For those of you who are maybe coming from finance, this would be maybe the setting of kind of a minimization version of Bermudan options pricing, but I won't go into that. Okay, so questions about the setup?
So
Yes.
here you're allowing the cost of stopping at time t to depend on the previous time steps also. Is it
Yeah, so it's non-Markovian. It's totally general. Yeah, history dependent also. Yeah. Great. Other questions?
I guess that last notation there, if you've not seen stopping time, that just means it's a function of all the information you've given. Any function of all the information that you've given, whether you stop it. Anything which looks at that and says stop or not. So when all such functions, you want to minimize that.
So you're searching for F such that evaluation of that.
No, we're searching for a strategy by which you decide when to stop.
But the set of strategies is what kind of thing?
Yeah, so a strategy is this for, yeah, good. So a strategy is the following. For each t, it's a mapping from every possible set of t high-dimensional vectors that you could possibly see to 0, 1. Where 1 would be, I stop now if I haven't stopped yet. Yeah. Thank you, Steve. Make sense? Great. Other questions? Great. Okay, so I guess what I'll do with the remaining time, that I'm happy to take other parts of it offline. I claim to you that the key intuition of our approach is sufficiently simple, perhaps, now maybe I'll deeply regret saying those words, that I think in the remaining time I can more or less explain to you the key idea of what's going on, and then maybe offline I can talk about more details about algorithms and other connections, etc. Great. So, okay, I do need to take a poll. Can you raise your hand if you at least are vaguely familiar with the basic definition of a martingale? Okay, so most people, so if you are not, then I will do my best on these slides, and I'm happy to take questions, but some of it might be a little bit hard to grasp if you have no familiarity with martingales, but I'll try to make that, fill that gap in to the best that I can here. So, okay. So we're going to start with just a bit of notation, a definition. I'm going to define the best you can do to be opt. Okay, so there's nothing that's a simple statement, just a definition. Okay, now we're going to get 40% of the way there with a completely silly observation. That's actually going to be 40% of the whole thing, is this line here. What is this line here saying? This line here is saying the best I can do if I have to play by the rules of the game I just talked about can't possibly be better than the following. Suppose I get to look into the future, and I get to literally see which one is the best place to go. This would be like saying, suppose in the secretary problem, you got to cheat and look at all the values you were ever going to see. And you pick the best one. And then the best, how good you would do an expectation there would be expected value of the minimum of all the z's. So that one inequality is the completely silly observation that if you have to play by the rules and decide online in real time whether to stop or not, you can't possibly do better than the expected value of if you got to look at everyone and actually pick the smallest. A simple observation. And of course, this simple observation appears in many papers and connects to these things called the profit inequalities and these kinds of things. Incredibly, we're 40% of the way there. Now, I'm going to use one of the more elementary results from the theory of martingales, where if you have never seen a martingale, I'll try to give kind of at least some intuition about what that is, to turn this inequality into an equality, and then we're 80% of the way there. Okay, so I'm going to turn that inequality into an equality through a single application of the so-called optional stopping theorem. So let me remind people of a few things very quickly. So a martingale is a process so that where you expect it to be next, given where you are now, is where you are now. That's effectively the definition of a martingale. And what does the optional stopping theorem say? It says the expected value of such a process evaluated at a stopping time. So you're not going to look at that process at time 1 or time 2. You're going to look at it at a random time, where that random time is effectively, one of these types of stopping times that we've been talking about. It turns out the expected value of that process at that random time has to be equal to the expected value of that process at time 1. This is this so-called optional stopping theorem. We're going to use that one time here. How are we using that? How have we turned this into an equality? Here's what we're going to do. Let's think about a new stopping problem. That's going to be what's written here. We're in this new stopping problem. If I stop at time t, I don't get zt anymore. I get zt compensated, namely minus my best guess of the all-time min of the z's, given ft, given what I've seen so far. So let me say that again. Here we're going to be looking at a new stopping problem, where when I stop, I don't get zt, like in the original one. I get zt minus the expected value, the conditional expected value of the all-time min of the z's, given what I've seen so far. That's why in this new problem, if I pick strategy tau, I get z tau minus the conditional expectation of the all-time min, given the filtration up to time tau. That's called the dude martingale associated with the all-time min of the z's. Okay, now why do I claim that somehow that turns this whole thing into an equality? It's because, as I said, for any stopping time whatsoever, if I evaluate this dude martingale at that stopping time, I cannot do better or worse in expectation than if I just looked at this martingale, namely E of min given f1, E of min given f2, E of min given f3, at time 1 and took the expectation. But that just gives me this term here. And in particular, because of the optional stopping theorem, namely that for any martingale, and thus also the martingale E of all time min given ft. If I stop according to such a stopping strategy tau, I cannot do better or worse in expectation than if I just had taken the expectation stopping at time 1. This term here and this term here exactly cancel. And so we simply are effectively left with opt equals the best we can do on the original Z process. Okay? That's kind of the key, that's a very key, it's in some sense, pretty simple in the grand scheme of martingale arguments. If you've never seen martingales before, it would likely not be simple, and I apologize for that. Let me give people 10 seconds to just see if they can place this in their mind, and I'm happy to take any questions about that, because it's really, we're then 80% of the way there.
So which terms on the right-hand side are easy to compute by simulations, and which ones are hard?
I'll make that clear in a moment.
Okay.
Yeah. I'll make that clear in a moment. Yeah, let's first let's get the equality in our minds, then I'll connect it to the other stuff. Yeah, thank you. Okay, any questions about why that is an equality? Okay. Now all I'm going to do is rewrite this so it's a little bit clearer. Let's call our original process Z1. Okay? Z1t. That's just our original process. Now I'm going to define a new process, Z2, where Z2 at time t is our original process compensated by, or really minus, our best guess of the all-time min given what we've seen up to time t. Okay. In which case, all I have written here is that the original optimal value, defined to be the best I can do stopping on the Z1s, is equal to the expected value of the all-time min of the Z1s plus the best I can do if I have to do stopping not on the Z1 process, the original one, but on this new Z2 process. Okay? So this is simply a restatement of what I have up here. And now to begin to answer the question asked in the back, all I'm claiming so far is that E of the all-time min of the Z1s is easy to compute by simulation. Why is that? Because I can simulate a trajectory of my information process, evaluate G of the Ys at each of the times, get a sample, and do this 1 over epsilon squared times to get an epsilon approximation by some strong law kinds of things like this. Other questions about, because we really have almost all the ideas in place, even though it seems very simple.
Can you repeat why it holds with equality?
Yeah, so the point is, for any martingale, so this is a martingale, right? Now for any martingale, no matter which stopping time I pick, the expected value of that martingale evaluated at that stopping time is equal to just the expected value of the martingale at time 1, which is just going to be E of min. So even if I optimize over stopping times, that will be true for the best stopping time, it's true for any stopping time. And thus, since it doesn't depend on my selection of stopping time, even though I'm optimizing, then these things are going to cancel. Thank you. Other questions?
Do you have any hope when you have an infinite horizon?
Yes, so that, the answer to that is yes, although the algorithmic part has to be restated a bit because we make no assumptions whatsoever. So as far as efficient runtimes, you could create a bogus process that says for the first trillion periods, it's garbage. And I rig it so something interesting but certainly if there's a discount factor or you wanted to make some kind of assumption about, yeah, but let me answer that offline maybe. But the answer is effectively yes.
So the only place finiteness was needed was to use optional instructions. So if you knew
Oh,
tau was gone,
yeah, for here it's not needed at all.
So this all would work for you. As long as you knew tau was.
As long as tau is almost surely finite because your process had some, some meaningful thing. As far as the algorithmic statements, you have to be a little careful.
Like, can you compute the minimum?
Yeah.
That's
Yeah, that's right. Thank you. Okay, good. So as I said, we're kind of 80% there. Now the one clever thing that we're going to do is realize that, well, this is just another stopping problem. So I can apply the same exact logic and bootstrap it on this error term here. In which case I find, just literally applying, let me do that in slow motion. I solve you on this. But right as we just, in this discussion further fleshed out, my ability to apply this logic to a stopping problem required nothing whatsoever, effectively. No assumptions whatsoever. And so I will simply apply exactly the same logic to this new stopping problem which popped up in the remainder. In which case I will define Z3 to be my Z2 process minus my best guess of the all-time min of the Z2 process up to time t. And I go through the same, literally the exact logic, and I find my original optimal value is the expected value of the min of the Z1s plus the expected value of the min of the Z2s plus the best I can do on the Z3s. And so, Alex, speaking to your question then, as I'll point out when I actually write out the expression, I claim E of min of the Z2s, you can also compute by simulation with one level of nesting. One level of nesting. And in fact, the min of the ZKs, where if we just apply this logic kind of recursively, as long as we can show the error dies off, which it does, we get that the optimal value of the original problem is E of the min of the Z1s plus E of the min of the Z2s plus E of the min of the Z3s, etc. And each of those E of the min of the ZKs can be computed entirely by simulation with only K levels of recursive nesting. Which means when K is large, it's bad, but for any kind of like fixed K, you can do it and it doesn't scale with the time horizon. I'll make that more precise in a moment, but the point is the things you can simulate are E of the min of the ZKs. Let me put the expression up, so good. So let me convince you of roughly what this looks like, okay? So I said the first term is just E of the min of the Z's. You know, clearly this, you could just watch the process, compute for each thing G of this, G of this, G of this, take the minimum, you get a sample, and you do this some number of times. Okay. What's the second term? What's E of the min of the Z2s? I claim E of the min of the Z2s is this. Instead of simulating the original process, I do this. At each time, I compute the Z for where I am, which is like what I had to do before, but now there's another level of complexity. I have to compute a single conditional expectation. Namely, I have to compute what is my best guess of the all-time min given what I've seen now, which does create one level of nesting. Because at each time, I have to get an estimate of this conditional expectation. Okay, but it's one level of nesting, we can do it. The next thing has two levels of nesting. Worse, but it is still kind of completely symmetric, it's just the thing composed with itself, etc. So you say, okay, that's symmetric, that's nice looking maybe. I understand that roughly each of these things is some kind of conditional expectation. For the first two terms, it's kind of very clear. I can believe that if you only go out to a few terms, you can control the level of nesting as just third term is step 3, fourth term is step 4. Don't worry about parsing this exactly, but what I've said is true. So what? The key is this. What we are able to show is if you truncate that procedure after k terms, and for example, suppose that with probability 1, your Z process is upper bound, has some with probability 1 upper bound, I'll call it U, then the error, the gap between the optimal value and the sum of the expected values of the min of the Z1s, the Z2s, or the ZKs shrinks like 1 over k. The simplest bound you can get is like U over k if it's between 0 and U, so it's relative to an upper bound, although in the paper we also get results if there's no upper bound in terms of some kinds of moments and things like this. What's the key insight from this? The key insight from this is that for the first time, we have a method so we can rigorously control the error independent of the length of the time horizon. In particular, the level of nesting that we need to get a guarantee on how far off we are does not require us to do backwards induction starting at the end and go nest, 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 so you get a level of nesting that scales with the time horizon. Here, if you want to be within 25%, you need to go to depth 4, independent of the time horizon, nothing to do with the joint distribution of the y's, nothing to do with the dimension whatsoever. And that is the key enabler of us to get then polynomial time methods. It's all based on exactly this idea. It's not that hard to analyze how you do the nested simulation of that process. This is really the key idea. To get a stopping strategy, you roughly leverage this. You could, even though it's not exactly true, you could think about, well, I just do kind of this to approximate a value function, and you need to tweak that a bit for it to actually work, but it's all built on this exact idea. If you followed me so far, then you effectively have 90% of what's going on, and the rest is kind of more or less how you think it might go. With the last 2 minutes, let me quickly jump to the connection to max flow min cut, and then I'll wrap up and we'll have time for questions. Is that okay, Alex? Okay. So I'll jump over, this is the convergence proof, some algorithmic implications. Okay, so let me jump to what I'll call the max flow connection and Martingale duality. So what I'm now going to convince you of is, and again, it's incredibly intuitive, it's somewhat surprising that it had not been brought to light and used elsewhere in the literature. I'm going to convince you of a correspondence between this optimal stopping problem and what's called the min-cut problem. If you're not familiar with min-cut, you'll see intuitively what it is in a moment. What does optimal stopping say? It says for every possible trajectory of this high-dimensional information process, I need to pick a time t to stop. Right? That's what it says. What is min-st cut? So min-st cut, I'll give a 20-second introduction to min-cut. Suppose you have a network, which is a graph with nodes and edges. There's a special node marked source and a special node marked sink. And suppose every edge has a non-negative weight on it. Then the min-st cut problem says, can I pick a set of edges that separates all paths from S to T, namely if I remove those edges, there's no more paths from source to sink in my network, such that if I add up the weights of those edges, it's as small as possible. Okay? Since you have to disconnect the source from the sink, it's hard to pick a small set of edges in some sense, because you need to disconnect these things, so there's a tension there. That's this canonical operations research network problem called min-cut. Let me reframe what I just told you. Namely, instead of saying I need to pick a set of edges that disconnect source from sink, another way to say that is for every path from source to sink, I have to make sure at least one of my edges cuts that path. Which, if you just kind of think about it for another minute, you would come to the conclusion, this is simply saying, I need to make sure that for every path from source to sink, I have selected at least one edge to cut the path. But if we think about it this way, and we were to conceptualize a network where we had kind of a path from source to sink for every possible high-dimensional trajectory of our information process, we'd see that even just kind of conceptually in words, these two problems are completely equivalent. And it turns out there's kind of a very natural way, which I'm happy to talk about after the talk, to rig the costs of these edges so that you can create a one-to-one correspondence between these cuts of edges, which you might want to select to disconnect S from T, and the expected value of a stopping strategy you might implement to decide when to stop on this process. Namely, let me say that a little bit. So there is a way, for a given optimal stopping problem, there's a way to cook up a network so that you kind of create a dummy source and a dummy sink. You've got a path from the source to sink for every possible trajectory of that high-dimensional Y process. So it's a massive, massive, massive network. Okay? And you can rig the costs of the edges so that for every ST cut, namely for every way to select a set of edges that disconnects S from T, that can be put in exact correspondence with a stopping strategy so that the expected value of that stopping strategy is exactly the same as the sum of the costs of those edges. That takes a little finagling, but it's actually pretty straightforward, but I won't be able to go into those details right now. And so, yeah, I guess that's pretty much what I wanted to say. Maybe I'll end there. Let me simply quickly, let me jump to a conclusion. So just a few things about future work. So one thing that's definitely on our minds is to create a fast implementation of this that's actually really kind of compare carefully to other kind of methods that are out there on kind of real financial data and kind of actually producing usable code. This is the first thing I've ever done where I really think it could actually be really useful to people that want to solve these problems. And one thing we're working on is kind of faster expansions and smarter ideas and other connections to network flows to make it not only the first thing that can work for truly massive problems, but to also make it very effective even for small problems. We're currently thinking about a lot of generalizations to other problems in finance, control, OR, and stats, including multiple stopping and swing options, high-dimensional dynamic pricing, connections to choice models, connections to sequential statistics and change point detection, connections to profit inequalities and economics. There's very interesting, robust, and strategic variants of optimal stopping that our work should speak to, but we don't really understand. One thing that's very much on our minds now is how we apply this to online matching and other combinatorial problems. And just kind of one interesting potential application is to applications of kind of changing dosages in various healthcare settings. And there's people that kind of work on that. So, as I said, we're trying to come up with smarter expansions. One very interesting thing that comes out of this work is that for online high-dimensional optimization problems, really not a lot is known as far as lower bounds and formal computational complexity in the sense of Turing machines, NP-complete, etc. There's a little bit known. It's kind of seminal results of like Titsiklis and a few other people. But in our opinion, it was very surprising that even though there's all this work on high-dimensional optimal stopping, there is, in a formal sense, kind of a polynomial time approximation scheme for this, which was not previously known. And this kind of begs the question of what other surprises are lurking there. Interestingly, our methods also yield faster methods for certain kinds of really, really big network flow problems. We actually think there's really interesting connections there to certain notions of parallelizable algorithms for flows and other methods. We don't know where this could end up. And I'll leave you with the following really big question, which I know several other people, including Sid and various others, are working on, which is, when is high-dimensional control actually tractable? A lot of my career to date can be roughly described as trying to beat the crap out of recursive dimensionality. I continue to do so. But it just keeps yielding interesting surprises, and it seems we really don't know that much. Again, if people have any interesting thoughts on this or other places you think it might be applied, please shoot me an email, and I'll end there. Thank you so much.
Surely we have a few questions, okay?
Who do you find? I mean, what does the network look like when you are saying that network that finding?
What is what?
When you were talking about the cut.
Yeah, so it's literally a tree. It's in fact a tree network where there is a path in the tree for every trajectory of the y's, and if two trajectories of the y's agree on some part of it, then they overlap in that part of the tree. So it's really quite simple then. And in fact, how do you rig the costs? The cost of a given edge is effectively what's the probability that I have gotten here times what's the cost if I stop here. That's it. Alex, please.
So to continue this same question,
Yes.
what are you getting out of this new language?
Good. So we get two things. So one, we get a new interpretation of like many duality results in the mathematical literature for this problem. So that's one thing we get. And it unifies, in fact then, again, even though there was this vast math literature and kind of using various sophisticated arguments to get different slices of kind of duality results there, we actually recover almost all of that through literally just max flow min cut. So that is interesting in its own right. I would say from our perspective, it has been very useful in suggesting what more complex control problems might be amenable to this approach. So as far as the optimal stopping itself, it's not necessarily on the critical path to deriving the first order results, but I'd say it is highly suggestive of how maybe this approach could actually go way beyond optimal stopping. Thank you.
Maybe I'd like just follow up. One sort of core idea in anything in an MDP is that a forward algorithm should never work. You must do a backward induction in order to get the optimal policy. What I think this is suggesting is that you can do a forward algorithm as long as you're willing to give up something. This is sort of exactly characterizing that at each time if you run a forward algorithm, how many iterations of a forward algorithm do you run? It's not going to be optimal, we know that, but you can bound how much loss you're getting. So in that sense, it feels like at least one of the first results in that here in a very general MDP, a forward algorithm, it can never be optimal, we know that, but it is near optimal.
What was the acronym you used?
Oh, so
Markov decision.
MDP is Markov decision process, sorry.
My question was on the language of...
It was the flows, I think he was asking about
yeah,
the flows.
yeah,
Yeah,
but in
okay.
that max flow rather than...
Yeah, maybe we'll just continue. Arthur, please.
I got stuck at 40%. If you think it
Sure.
would be illuminating or useful, can you explain what your algorithm does for secretary problem? What it would look
Yes, I could. So for secondary problem, it would do this. The first term of the expansion would just be, say there were IID uniforms, right? It would be E of the min of T IID uniforms, which is, I guess, like 1 over T or something like this, or 2 over T, or 1 over T, I think it's 1 over T. Now, what would the next term be? For the next term, it actually already gets complicated and interesting. It's E of the min of the following. What is the first term appearing in the min? It's the value you're looking at minus my best guess of the min of all of them, given the one I've seen. What's the second term appearing in the min? It's the one I'm looking at minus my best guess of the all-time min, given the 2 I've seen so far. What's the third one? It's the one I'm looking at minus my best guess of the all-time min, given the first 3 that I've seen. And it's not an entirely trivial object, E of the all-time min of them, given the first 3 that I've seen. You can simplify that sum, but that's what the second term becomes.
So if you were to rigorously compute that sum, would it be equivalent to dB or not?
If you could what?
If you were to write down the whole sum, which has t terms, right? Or
What do you mean, is that equivalent?
oh, it's infinite sum. Never mind. There's no
Yeah,
way.
interestingly, if you don't, you can modify it slightly so it converges in T rounds, but if you want it to go all the way, as I've stated, it would actually not necessarily converge there. Yes?
Okay, thanks.
Yeah, so in the very beginning, you mentioned some PD-based method.
Sure.
So do you really mean you can sort of overcome dimensionality by PD-based?
No, my approach has nothing to do with PDEs.
Yeah, no, I mean, like for that specific method. Because as far as I know, PD also solves the problem.
Yeah, no, PD, I mean, those are 4 methods that people have largely used to come up with heuristics, I would say.
Yeah, it's like irrelevant for this, but
It is irrelevant for this talk. Yeah, no, those were, I wrote down kind of several of the main approaches that people in the literature have taken to attempt to tackle this problem. But again, to our knowledge, this is the first that really comes up with a polynomial time approximation scheme type method. Yes?
So does the minimum cut correspond to the optimal policy and near min cuts correspond to near optimal
Yes,
policies?
that's effectively true. Yes.
And do you have a way of mapping your policy and the optimal
Yes,
subset
yes,
that
in
you
fact,
do at
yeah.
Congress?
So those Z's effectively correspond to residual capacities in some appropriate way as you get to the higher K's. In fact, to put it another way, for a large K, ZK is the residual capacity of the arc corresponding to the history that I'm looking at, subject to me having done a few iterations of a flow method which can correspond to that kind of expansion that I was talking about. More questions? Yes?
Any attempts to do the same for different risk measures?
Good. So, as long as it can be expressed as
Translate the question.
what? Oh,
Restate the question.
yeah. I'll restate the question. So, the concept of risk measure says instead of trying to optimize an expectation, suppose you wanted to optimize something that's like penalizes the variance or something like this. So my first order answer to that would be the following. If it can be expressed as the expectation of some perhaps different stopping problem, then you're fine because it can be put in this framework naturally. If not, then it's less clear, but something should be doable there. That would be my answer to your, so in other words, if it could be expressed as like wherever you stop, you get the square, the variance of the value at that time plus some other thing, then that would be okay because it would be expressible in terms of a functional of the value you're stopping at. But there would be other ways to ask the question that you did where it would not be able to be written that way, in which case it would be less clear to me, although I would suspect, and I thought about something like that a little bit, and one could attempt to combine this with some kind of Lagrangeifying certain kinds of constraints corresponding to whatever the risk measure was steering you towards, where maybe there'd be a way to make it work also.
So you're describing something like optimizing the expectation with a chance constraint. I don't know.
Something like, yeah, there would be, there's definitely a thought that extensions along those lines should be doable, yes. Thank you.
Yeah, I guess, sorry. I guess now that you had this as a cut problem, what can you say about linear programming? Like,
well, good. So the problem is the number of variables is a
yeah, but is there no oracle that runs in polynomial time that, so what's...
To our knowledge, the fact that you can think about doing this by simulation in that way. So the point of polynomial time here, you can't even be logarithmic in the number of variables because there's effectively infinity of them. The whole point is, one of the key insights of our approach, and I am pretty aware of all the literature on fast linear programming and distributed linear programming and all those kinds of things. I believe this way to think about it in terms of access to a simulator, which then effectively, by very cleverly aggregating information through your simulations, is implicitly solving the LP or flow problem. To our knowledge, this is the first such method, and so no, I do not believe there's going to be some kind of ellipsoid thing that would be able to in any way mimic this. Interestingly, there are some old flow papers in the distributed algorithms literature which, although in a very different context, get at ideas which are, I'd say, metaphysically related to what we do, and understanding that more precisely is something that's very much on our minds. Thank you. Other questions? Okay, then thank you again. Thank you.